Hi, folks. Today we're going to talk about set theory. So, set theory is one of the most fundamental underlying structures in mathematics. And pretty much everything we're going to do the rest of the semester is based on, at least at some level, this idea of set theory. The axioms of set theory are the axioms which describe the majority of mathematics. When we think about set theory and what set theory is all about, at a most basic level, it's asking, how can we collect objects? Are there ways of comparing two collections of objects? And what rules should we establish for analyzing these collections? Again, most other branches in math, they're built on set theory as a foundation. And so when we are looking through everything else the rest of the semester, it's all tied back to this idea of sets. So what is a set? Well, a set is a collection of well-defined, distinct objects. The objects in a set are called elements. And so well-defined means that individuals have a clear understanding of what the object is. If we are talking about a dog, well, there's a ton of dogs out there, and so you have to be very clear about a dog. You would say, oh, it's Jennifer's dog, and hopefully Jennifer only has one dog, in which case that is the well-defined object, the dog that we are talking about. Distinct means it does not contain the same object twice. And so we're not going to be counting Jennifer's dog twice. Whenever we're dealing with a set, it only contains elements which are different from one another. Objects could be numbers, geometric shapes, fruit in a basket, other sets, Jennifer's dog, whatever. I don't even know who Jennifer is, but her dog is a part of this now. And so let A be the set which contains the numbers 3, 4, and 5, just as an example. In symbols, we could say A is equal to the set containing 3, 4, and 5. We have the curly brackets to denote that this is a set and that these are distinct values within that set. If we wish to say that 3 is an element of the set A, we would write it like this. 3 is an element of A. If we wish to say that 7 is not an element of an A, then we could say that 7 is not an element of A. Sometimes our sets are messier, and so in that case, we may use set builder notation. Set builder notation is written in this format, where we have curly brackets to distinguish that we're dealing with a set of objects. Then we have what the objects look like, followed by a vertical line, and then whatever descriptors are needed to describe that object. And so in this case, set builder notation is saying the set of all x such that x is less than 8 and x is a real number. A common example is the rational numbers. We can describe the rational numbers as the set Q is equal to the set of all things P over Q, where P is an integer and Q is a natural number. And this is where we can start using the number sets that we discussed previously, because we're going to be describing sets in terms of other sets. The cardinality of a set is the number of elements in a set. In symbols, the cardinality of a set can be written like this with the absolute value bars. And so if A is equal to 3, 4, 5, then the cardinality of A is 3, because there are 3 elements. The empty set is a set which has no elements. In symbols, this can be written as a circle with a line through it, or occasionally as this, just a pair of brackets with absolutely nothing written there. It has a cardinality of 0. So cardinality can also be defined for countable and uncountable infinite sets, although it can get a little bit more complicated. The cardinality of the natural numbers is this symbol, which is pronounced Aleph null. Going beyond that can be contentious in set theory, since set theory is viewed as a branch of discrete math, which means we deal with countable things. Subsets. If A and B are sets, B is said to be a subset of A. Written, B is a subset of A, or sometimes B is contained within A, if every element of B is an element of A. So it works the way you would hope it would. And so if A is equal to 3, 4, 5, and B is 3, 5, then B is contained within A. B is a subset of A. If B were not a subset of A, we can write that as B is not a subset of A, or B is not contained within A. In the case of our standard number sets, the natural numbers are contained within the integers, are contained within the rationals, are contained within the reals, are contained within the complex numbers. By definition, any set is a subset of itself because they contain all the same numbers or same elements. The empty set is also always a subset. And so two sets are said to be equal if both A is a subset of B and B is a subset of A. This is written A equals B. If they're not equal, we say A is not equal to B. Now, this is important because this is one of our first times of trying to address what it means to be equals. And we're going to go in depth into this idea of equality very soon. And so if B is a subset of A and A is not equal to B, then we can say that B is a proper subset of A, which is written B is contained within A. So B is a proper subset of A. If B is not a proper subset of A, this can be written as B is not a proper subset of A. Now, sets can include sets within them, and we will often see this as the case. And so the set C, which has 1, 2, and the set containing 3, 4, is a set which has 3 elements. It has 1, it has 2, and it has the set containing 3, 4, which counts as a single element. And so looking here, 1 and 2 are both elements of C, and so the set containing 1, 2 is a subset of C. 3, 4, the set containing 3, 4 is an element of C. The set containing 3, 4 is in fact a subset of C because, well, if we just have a set which has the set containing 3 and 4, this has the set containing 3, 4 in it. So this would be a subset. The set containing 1, 2 would not be a subset of C. Weird things can happen, particularly with sets involving the element empty set or the set containing the empty set. This can get weird. We'll see how weird soon enough. If A is a set, then the set whose members are all of the subsets of A is called the power set of A and is denoted with this curly P and A. Consider A equal to 3, 4, 5. Then if we wanted to create the power set, that would be the set which has all of the subsets of 3, 4, 5. And so the empty set and the whole set are included in there. 3, 4, and 5 as individual elements in a set are included. And then we also have 3, 4, 3, 5, and 4, 5. And so this is all of the possible subsets of A. The power set will always contain the empty set and the set itself. And so here's a weird looking true-false practice. And so consider the set E, which is equal to the empty set and the set containing the empty set. Answer the following as true or false. And so here are a whole bunch of questions. If you want, you can go through them all real quick. What I might recommend is write out the power set so that you can check and see if these are elements or subsets. And here's our answers. And so is the empty set an element of E? Yeah, it's right there. Is the empty set a subset of E? Yeah, the empty set is a subset of every set. Is the set containing the empty set an element of E? Sure, it's right there. Is the set containing the empty set a subset of E? Sure is, because the empty set is an element. Is the set containing the empty set an element of E? It is not. And then is the set containing the empty set a subset of E? It is, because this is the set containing the empty set. And so a set containing this element would be a subset of E. When we think of the power set, it's very similar and very messy and tricky to wrap your head around, but there are your answers if you'd like to play with it a little bit. The next big thing is unions and intersections, and we deal with unions and intersections a lot. And so let's make sure we understand the core idea. Let A and B be sets. The union of A and B, written A union B, is a set of all objects which belong to either A or to B. And so if something is in either one of them, it's included in the union. The intersection of A and B, written A intersect B, is a set of all objects which belong to both A and B. And so for the intersection, it has to belong to both of them. If it's not in both of them, then it is not included in the intersection. If the intersection has nothing in it, it's just the empty set, then the sets are said to be disjoint. Now, sometimes there's going to be more than one operation being used, and in that case, we would use parentheses to denote the order of operations. These ideas of unions and intersections, they're binary operations, which means they're taking two things and giving you a new thing. You can use parentheses to figure out the order. And here's an example. Let A be 2, 3, 4, B be 3, 4, 5, 6, and let C be 6, 7. Then A union B is going to be 2, 3, 4, and then 2, 3, 4, 5, 6, or sorry, and 3, 4, 5, 6. Well, if this includes everything from both of these, you have to have the 2, 3, 4, and the 5, 6. The intersection is saying, what do A and B have in common? Well, the elements A and B have in common are 3 and 4. When we look at A union C, well, A union C would have 2, 3, 4, 6, 7. If we look at B intersect C, well, B and C, they only have 6 in common. And so that's the only thing in B intersect C. A intersect C, well, they have nothing in common. And so that's going to be the empty set. A union C intersect B, well, A union C we know is 2, 3, 4, 6, 7. And if we are intersecting that with 3, 4, 5, 6, then we're going to have a 3, a 4, and a 6, which they both have in common. A intersect B, union B intersect C. Well, that's going to be the 3 and the 4 and the 6. Note that they both give the same value. There might be a rule involved in that. We then have A union the empty set, which is just A, and A intersect the empty set, which is the empty set itself. Another concept we sometimes play with is the universal set and the complement. So if for a certain problem, all of the sets being considered are subsets of a given set U, then U is called the universal set. Essentially, it's like the domain. It's saying this is the set of values we're playing with. And yeah, it includes everything. The universal set can be thought of as a set which contains all of the relevant elements for a particular problem. Universal set will change from problem to problem. So be aware of that. There is no one universal set. Every single problem you encounter has a different universal set. Given sets A and B, the complement of A relative to B is the set of elements in B which are not in A. Often this will be written B minus A. And so essentially we're just taking the elements in A and removing them from B. If U is the universal set, then the complement of A, written A prime, or U minus A, is the set of elements in U which are not in A. And so here's an example. If you let U be equal to 1, 2, 3, 4, so the entire set is 1, 2, 3, 4, and A is 1, 3, 4, then the complement would be A prime, which would just be the set containing 2. The complement is just all of the elements not in your set. Provable properties. There are a lot of provable properties. This is just a handful of them. These are kind of the big ones. And so let A, B, and C be sets. Then the empty set intersect A is always the empty set. And the empty set union A is always A. We know that A intersect B is always contained in A, and it's also contained in B. A is a subset of A union B. A union B is equal to B union A. A intersect B is equal to B intersect A. And then we have a few which look a little bit more complicated. So if you take A and you union it with the union of B and C, then you get the same thing as A union with B union with C. Essentially, this is saying we can take the union across 3 things. We can take the intersection across 3 things. A union A is equal to A intersect A is equal to A. And then if A is contained in, or if A is a subset of B, then A union C is a subset of B union C. And the same goes for the intersection. Essentially, that's a way to restrict something if we need to. We also have properties related to the complements. And if you'd like, here they are. And then we also have ways of kind of distributing these things. And so A intersect B union C is equal to A intersect B union A intersect C. A union B intersect C is equal to A union B intersect A union C. And these are fun to play with. What I would recommend is create a few lists of numbers and see if you can demonstrate all of these with your sets of numbers. You could even go back and use the sets that we had up here. 2, 3, 4, 3, 4, 5, 6, and 6, 7. Now, I mentioned at the beginning that this is an axiomatic approach. When we think about set theory is the base rule set that we play by. And even this base rule set has rules. And here are the 10 big axioms that we accept when we're dealing with set theory. And so, for instance, the axiom of extension. If A and B are sets, and if, for all x, x is an element of A, if and only if x is an element of B, then A is equal to B. And so this is a way of just determining if something is equal or stating what it means to be equal. We have similar axioms describing a number of different things. Some of them we often will say, hey, maybe it's not true. For instance, the axiom of choice. If A is a set, the elements of which are non-empty sets, then there exists a function f with domain A such that for members B of A, f of B is an element of B. It's a complicated one, but it's one which we often ask questions about, saying, if we don't have this axiom, what happens to certain fields? But it ends up being that we get different approaches to mathematics depending on which axioms we set as true and which ones we set as false. Generally, we treat these axioms as our go-to. And so whenever we are playing with most math, this is the set of axioms we are playing with. The reason for that is we had a previous idea of set theory, and it had a lot of paradoxes in it. The Zermelo-Fraenkel axioms cleaned up all of those paradoxes, and it made it so that math works fairly cleanly. And that's kind of nice. Final thoughts on set theory? Well, sets are the foundational structure and a structure we've always used. All of arithmetic is just playing with different sets of numbers. Now that we have the language of set theory, though, we can start doing more abstract things with sets. In particular, topology and graph theory. These are two of the most important branches of math for just about any field. Topology focuses on structures which are made from unions and intersections of sets. And so how do we group things together, and then how do we compare these groups to one another? Graph theory focuses on the idea of connections between elements. And so how can we connect ideas? How can we connect information? And so topology and graph theory, these are very, very important, and they naturally follow just the basics of set theory. And so now that we have the basics of set theory, we're going to be able to introduce the concepts from topology and graph theory without too much trouble. What types of collections of objects do you deal with in your life, and how do you analyze them? Good question. With that, I'll let you get to work exploring where you find sets and set theory in the real world. Good luck, folks.